The motion of waves is called simple harmonic motion, and simple harmonic motion refers to any oscillatory motion where the restoring force is proportional to the displacement. I don't know that we've seen this yet, but let's take, for example, a spring. So if I have a spring, the spring exerts a force on the mass, and that force is given by some spring constant times the displacement. So the farther I stretch a spring, x, the greater the force is. This force is the restoring force. It's going to restore my spring back to its equilibrium position. That's its resting position or its relaxed position. But the more I stretch that spring out, the greater that force is. And so that's a good example of a restoring force that's proportional to the displacement. That's going to be true too, by the way, for our medium. Like let's say, for example, I have a collection of air particles just in space. These air particles all have their particular position, but if I have a wave that comes about and pushes this particle out of its position, there's going to be a force, the force of the pressure of the other particles around it, that will force it back into that equilibrium position. So the farther that you remove that particle from its equilibrium position, the bigger the restoring force is going to be. There are several definitions that you'll need to know for simple harmonic motion, and those include amplitude, A. So if I imagine that I have a graph or a wave that looks like this, I'm looking particularly here at the axes where I have distance, I'll put this at y, and time, distance on the y-axis and time on the x-axis. So this is called a history graph. We'll see that a little bit later, but it's called a history graph. History graphs show the time history of a wave. The amplitude is going to be this distance, a. The period is going to be t. The time period is the time for the wave to go through one complete cycle. By the way, let me go back to that amplitude. It could be this distance as well. These are going to be the same, or this distance. Our amplitude for a constant frequency, or excuse me, our amplitude for a constant volume sound wave will always be the same. Amplitude is related to the volume. The period, t, is the time for one complete oscillation. One complete oscillation occurs when the particle has gone through one full cycle. And so a full cycle, it returns back to its original position. It starts here, goes up, and then comes back down again. Frequency is the inverse of the period. And so the frequency is 1 over t. Frequency describes the number of crests of a wave that pass in a particular time. So for example, if I have two waves, these are both history graphs, this one, in a particular amount of time, only 2 crests have passed. But here, I have 1, 2, 3, 4 crests have passed. So this wave would have a higher frequency. For sound waves, the speed of the wave is set by the medium. And the pitch is related to frequency. You're probably familiar with this, that a higher pitched sound has a higher frequency. High frequency is a higher pitched, low frequency is a lower pitched. This you might not be so familiar with, but it's very important that the speed of a wave is set by the medium. If it changes mediums, then it will change its speed. Okay? The speed of the wave is given by this formula. The speed is equal to the frequency times the wavelength. The wavelength should be a different kind of graph. Now this is going to look a lot like the history graph, but it's actually a little bit different. This graph looks a lot like the history graph. In fact, it might look the same, but it has different axes. This is the Y position, and this is the X position. Notice that the only difference are the X axes. Up here, I had the time, so it showed a particular point in a wave as it progresses through time. So let's say that you have a rope that you're waving up and down. This graph, the history graph, takes a particular point on that rope and tracks it as it moves up and down. Whereas this graph, a snapshot graph, shows the wave at a particular moment in time, not over a length of time, but at a particular moment in time, and then it shows the positions on that wave in that moment in time in a two-dimensional frame in the X versus Y. So I show you that because we need to know it in order to find the wavelength. The wavelength of a graph or of a plot of a wave starts at one point and goes to that same point. So this is one wavelength. Notice you can find the wavelength at different parts on the graph, like this is also one wavelength, or here, I would start here, which is on the downward slope here, and go over here, and that is also one wavelength. On the exam, I'll likely provide you a sketch of a graph and ask you to find the wavelength. One thing that students sometimes make mistakes with is they'll say that the wavelength is from here to here, but that's not true. That's actually half the wavelength. You go back to the same position. That is, here I'm on a downward slope, and here I'll be also on a downward slope. The speed of a wave, I said, does not depend on either the frequency or the wavelength. It depends only on the medium. That's something we've already said, but it's not intuitive, but it's very important that the speed depends only on the medium. So a higher frequency noise, a higher pitched noise, will not necessarily have a faster speed. But you say, you just gave us this formula and said that the speed is equal to the frequency times the wavelength, but now you're saying that the speed is not dependent on either the frequency or the wavelength. So the reason that is, this value is constant. It's always constant. Right? We've seen this before, where I have some constant value equal to the product of two variables. That means, for example, if the frequency of a wave goes up, then the wavelength goes down, and vice versa. If the wavelength goes up, the frequency goes down. Right? Let's go back to this thing that I showed right here. This is a low frequency, and this is a high frequency. Right? Here I have a low frequency. That means I'm going to have a big wavelength. And here I have a high frequency, or a big frequency. That means that I have a small wavelength. And if you remember what our wavelength is, this one actually does have a bigger wavelength than this wave. So here I have my wavelength here, my wavelength here. The frequency and the wavelength of a wave are inversely proportional to one another. In air, sound travels at about 340 meters per second. You don't need to memorize that number. It's just, I don't know, it's just an interesting number. Okay. Usually in musical instruments, I think this is probably always true actually. The larger the instrument, the lower the frequency. So for example, a tuba is much, much bigger than a piccolo. A guitar is a lot bigger, or excuse me, is smaller than a bass guitar. So this is I do my bass clef right? Is that a bass clef? I think that's bass clef. I can't do it. Anyway, these are different frequencies, and you can tell by the size. We'll talk about that in later in this section. Let's go ahead and look at the frequency of a mass spring system. That is, if I have a mass on a spring that's oscillating back and forth, the frequency of that is given by this, 1 over 2 pi, the square root of k over m, where k is called the spring constant. This is a measure of how stiff the spring is. So for example, you have springs on your car, right? That help to give smooth out your ride. Those springs, those pretty big, bulky springs. You compare those to say a rubber band. The springs on your car are going to have a much larger spring constant than a rubber band. They're both elastic materials. They're both springs in a sense, but the springs in your car have a much stiffer spring, so they have a higher K value. And then M is just the mass that I have on this spring. Notice that the length of the spring is not in this expression. Stiffer springs give a higher frequency. That is, if K goes up, that means the frequency goes up. We have a very similar expression. In fact, this expression will be more relevant for our study of the human voice production for a vibrating string because, effectively we have a vibrating string within our voice box. For a vibrating spring, like on a guitar, the frequency looks really similar to a spring. It's going to be T over mu. This is the Greek letter mu. Mu gives us the linear mass density. We've seen volume mass density, right? Rho was mass per unit volume. We've seen that already. The linear mass density is in units of not kilograms per cubic meter, but kilograms per meter. So this is a mass over the length. Um, L is the length of my string, or my vibrating string, and then T is the tension. So how does the frequency vary with these variables? Well, if the tension goes up, the frequency goes up. Right? That is a direct relationship. It's not a linear relationship, but it's a direct relationship. And then if the length goes up, the frequency goes down. So for example, a bass guitar has longer strings on it than a guitar, and so those longer strings can produce a lower frequency. Longer length gives a lower frequency.